Welcome girls. In today's lecture, we are going to see what is least upper bound and greatest lower bound and few theorems related to it. Before to see what is the LUB and GLB, we have to know some preliminary concepts. That is, we have to know what is bounded above set, bounded below set, and bounded set. Okay, so we'll see one by one. A set A contained in R is said to be bounded above if there is an element n belongs to R such that my set elements will be less than or equal to n. Okay, if there is an element n such that in my every element in my set are less or equal to that n, then I can say the set is bounded above. Okay, and it is said to be bounded below if there is an element m such that each element in my set A are greater than m. Okay, if it is greater, it is bounded below. If it is less, then it is bounded above. And a set A is said to be bounded if it is both bounded above and bounded below. If it is both bounded above and below, then I can say it is a bounded set. Always a closed interval m comma n will be a bounded set. Okay, we'll see some example. So suppose we consider the set of all positive integer. Positive integer means what? It will be 1, 2, 3 like that. Okay, am I able to find an element such that each elements are or will be less than the given element? No, it is not possible. But I can find an element, for example, I can find 0 so that my each element in my set of integers are what? It will be greater, isn't it? It will be great. Each element in my set, let me take it as says that x belongs to I. Okay, is 0 is the only element? No, I can find infinite number of elements, isn't it? I can find -1, -2, -3, all are what? Less than or equal to my x, where x belongs to the set of integer. So the set, this set can have infinite number of elements, so that those elements will be less than my elements in the set. Therefore, the set of integers will be what? Bounded below. It is bounded below and it is not bounded above. Okay, the set I of positive integer is bounded below, hence I is not bounded because it is not bounded above. Okay, so let me take one more example. Okay, if I take the example as that minus, so what are the elements? It will have -1, -2, -3, etc. Okay, now am I able to find an element so that the whole set will be greater than the given element? No, it's not possible. But I can find an element like 0. This 0 will be greater than or equal to, sorry, it is strictly greater than, okay, greater than the elements in Z minus, all the elements. Okay, I can have 1 is greater than 2, 3, etc. I can have an infinite number of element which is greater than the given set. Okay, therefore my set Z minus will be what? Bounded above. Z minus, the set Z minus will be bounded above. Okay, and as I said, any closed interval will be bounded. Okay, here the interval 0, 1 is bounded. This shows that boundedness and countability are different. Why 0, 1 is bounded? Because if I take 0, 1, I can find many elements like -1, -2, minus 3, etc., which are less than my given interval, closed interval 0, 1. If I include 0 also, then it will be less than or equal to. Similarly, I can find infinite number of terms which is greater than or equal to. For example, 1, 2, 3, etc. So, it is both bounded above, okay, as well as it is bounded below. Okay, since 0, 1 is both bounded above and below, I can say it is a bounded set. I hope you understand what is bounded above and bounded below set, and a set which is both bounded above and below are said to be what? Bounded set. Now we'll move on to upper bound. First we'll see what is upper bound, then we'll move on to least upper bound. Upper bound means if I have a set A contained R is bounded above, then that number n is called upper bound for the set. Okay, so in the similarly, if I am able to find an element m such that m is less than or equal to x, means then this m is the lower bound for the set. Okay, so if a set A is bounded above, and if I am able to find an element n such that if every element in the set are less than or equal to n, then it is what? The n is called upper bound of the set. Similarly, if I am able to find an element m such that m is less than or equal to, every element in the set will be greater than the given m, then I can say greater than or equal to. Okay, then I can say m is a what? Lower bound. Yes, so we'll see an example. So example is this. If I take I, the set of positive integer, just before we have seen that the set of positive integer is bounded below, but it is not bounded above. So how many upper bounds it has, how many lower bounds it has? It has infinite number of. Here the number -7, -6 are lower bound of I, and there are infinitely many number. For example, for the set of a positive integer, I can have 1, okay, 0, -1, -2, -3, etc. All are what? All the elements, these elements will be less than the given set. Therefore, there are infinite number of lower bound. Okay, similarly there will be infinite number of upper bound for the negative integer. That is, if I take b as a negative integers, that is -1, -2, -3, etc., then I can have infinite number of terms. So for example, I can have for the set b, I can have -1, 0, 1, 2, etc. Okay, these elements are what? Greater or equal to my given set of element in P. Okay, therefore this set is what? Bounded above, and I can these elements -1, 0, 1, 2 are called upper bound. Okay, I hope you understand. Next we'll see what is least upper bound. So least upper bound means you must have a set A. So the set a number capital L is a least upper bound if L is the upper bound and no number smaller than L is a upper bound for A. Okay, just before I have told you there will be infinite number of upper bounds and lower bounds for a given set, isn't it? Among that, for example, for upper bound, for this, you take this example, a set of negative integer. The upper bound for this negative integers will be what? -1, 0, 1, 2, etc. What is that least among the upper bound? -1. So for this set, -1 is the least element, minimum element, and this will be my least upper bound. Okay, so if number L, then this L is nothing but minus 1. For this set, my L is minus 1, least upper bound. Okay. So, for any set which is bounded above can have a least upper bound if that L is the upper bound. First, it has to be an upper bound, and no number smaller than L will be the upper bound of it. Okay, you should not have any other number smaller than L to be the upper bound for A. Then I can say it is a least upper bound. Okay. Next we will see what is greatest lower bound. Again, it's the same thing. If you have a bounded below set, okay, it must be a bounded below, and the number M, the small l, sorry, a number small l is called greatest to lower bound for A. If L is the lower bound, it must be a lower bound, and it must be the greatest among all the lower bounds. Then I can say it will be a greatest lower bound. Okay. Again, we have an example for the set of positive integer which is bounded below set. Here my lower bounds are what? 1, 0, minus 1, minus 2. I can have infinite number of lower bounds. Among the lower bound, the maximum, the highest first element will be what? Greatest element is what? 1. So, the greatest lower bound for my positive integer is 1. Okay, I hope you understand. We'll move on to the next theorem. This theorem is named as approximation property of least upper bound. In future, we'll be using by approximation property of least upper bound. You must remember there exists one member on the set which lies between L minus epsilon and L. What is L here? L is the what? Least upper bound. So, for every epsilon greater than 0, there exists one member of the set A which lies between L minus epsilon and L, where L is the least upper bound for the set. Okay, so that is what the approximate property of least upper bound says. So, we will see the proof. Suppose if there is no element between L minus epsilon and L, what will happen? Obviously, the element will be to the left of L minus epsilon. So, that means it will be every element on the set will be left of L minus epsilon. What does it mean? My x will be less than or equal to L minus epsilon. Okay. So, that means my L minus epsilon will be what? Upper bound for my set A, isn't it? But we have L to be the least upper bound. Will this least of the upper bound is L? Now we are finding a new element L minus epsilon which is still lesser than L, and that is the upper bound for my set of elements in A. Is it possible? No. Therefore, there will be surely one element between L minus epsilon and L. Okay. We'll see the theory part of it. So, if possible, assume there exists no element on the set lies between L minus epsilon and L. That is, all the elements of A lies to the left hand side of L minus epsilon. So every elements will be left of L minus epsilon. Okay, that means what? I will be having this relation, x is less than or equal to L minus epsilon. What does it mean? L minus epsilon will be the what? Upper bound for my set. Okay. So, L minus epsilon is the upper bound for epsilon greater than 0. We get L minus epsilon to be less than L, which is a contradiction. Why? By least upper bound axiom, L is the least of all the upper bound. Now we are finding new element L minus epsilon which is still lesser than L, and we are telling that it is the upper bound for the set, which is not at all possible. Therefore, this is not true. Therefore, our assumption is wrong. What is our assumption? There is no element between L minus epsilon and L. That is wrong. That means there will be an element between L minus epsilon and L. Okay. So, we have a note, the least upper bound of the set need not belong to the set. Sometimes the least upper bound need not belong to the set. For example, if we have for the set of integer I, my least upper bound is what? least upper bound will be 1, isn't it? And for the negative integer, the lower bound, the greatest lower bound will be what? -1. For a positive integer, it is +1, bounded below, so it is +1. Okay, so for the positive integer, +1 is the lower bound, and for negative integer, -1 is the upper bound. Okay, but for the interval 0, 1, what is the lower bound? What is the lower bound? Lower bound will be 0, but it does not belongs to the set since it is an open interval. Again, upper bound is 1, but it does not belong to the set since it is an open interval. Okay, therefore it is possible the least upper bound of the set need not belong to the set. We'll see the next theorem, approximation property of greatest lower bound. So for every epsilon greater than 0, there exists at least one member of the set A which lies between m and m plus epsilon, where m is the greatest lower bound of the set. Okay, so similar way we have to prove. So suppose there is no element between m and m plus epsilon. Where will be the elements? The elements will be to the right of m plus epsilon. So I'll be having like this. So m plus epsilon, m plus epsilon, then y. Now m plus epsilon will be what? Less than or equal to y, which means what? My m plus epsilon is the lower bound for my set of elements in A. Okay, but we know that m is the greatest of all the lower bound. Now we are finding a new element m plus epsilon to be the lower bound for the set, which is not at all possible. So our assumption is wrong, that is there will be an element, at least one element between m and m plus epsilon. Okay, and hope you understand the theorem. We have a note here again, as I told you, greatest lower bound of the set need not belong to the set. Again, for the open interval 0, 1, the least upper bound and greatest lower bound does not belong to the set. Okay, it is an open interval. Okay, yes, I hope you understand. We'll see you in the next lecture.